Good day, everyone. Today, we will tackle about adsorption.
So absorption is the process through which a substance originally present in one phase is removed from that phase by accumulation at the interface between that phase and a separate solid phase. Adsorption can occur at any solid fluid interface where molecules distribute themselves between two phases, one of which is a solid whilst the other may be a liquid or a gas. The molecules diffuse from the back of the fluid to the surface of the solid adsorbent, forming a distinct adsorbed phase. Good examples are your gas-solid interface and the liquid-solid interface.
And now for the definition. Adsorbate or solute is defined as the material that is being adsorbed, and adsorbent is the solid material being used as the adsorbing phase.
Types of adsorption. First is physical adsorption, also known as van der Waals adsorption. The individuality of the adsorbate and the adsorbent are preserved. It occurs when the intermolecular attractive forces between molecules of the gas adsorbent and the gas are greater than those between molecules of the gas itself. Next is Chem Absorption, also known as activated adsorption. It involves the formation of chemical bonds between the adsorbate and adsorbent in a monolayer, often with a release of heat much larger than the heat of condensation.
Here are some important key points to remember. Any potential application of adsorption has to be considered, along with alternatives such as distillation, absorption, and liquid extraction. Each separation process exploits a difference between a property of the components to be separated. As discussed, in distillation it is volatility, in absorption it is solubility, and in extraction it is the distribution coefficient. Separation by adsorption depends on one component being more readily adsorbed than another. It is recommended to use a selective adsorbent to which it separates on the basis of slight difference in mean molecular diameters. For example, N and isopentane have diameters of 0.489 and 0.558 nanometers respectively. When an adsorbent with pore size of 0.5 nanometers is exposed to a mixture of the gases, the smaller molecules diffuse to the adsorbent surface and are retained, whilst the larger molecules are excluded. In another stage of the process, the retained molecules are desorbed by reducing the total pressure or increasing the temperature.
The physical properties of adsorbents, usually in the form of pellets, beads, or granules ranging from 0.1 mm to 12 mm in size, composed of very fine pores with pore volume up to 50% of the total particle volume.
The common types of adsorbents are the following. Activated carbon, a char-like material with high surface area, usually ranging from 300 to 1,200 meters squared. Silica gel, a hard, granular, porous material made by precipitation from sodium silicate solutions treated with an acid. Activated alumina, aluminum oxide activated at high temperature and used primarily for moisture adsorption. Aluminosilicates, porous synthetic zeolites used primarily in separation processes. And synthetic polymers, these are made by polymerizing two major types of monomers.
The nature of adsorbents. Adsorbents are available as regular granules, pellets, and spheres. The size reflects the need to pack as much surface area into a given volume of bed and minimizes pressure drop for the flow of bed. An adsorbent should embody a number of features. It should have a large internal surface area and accessible through pores big enough to adsorb molecules. Adsorbents should be capable of being easily regenerated, not age rapidly, and should be mechanically strong enough to withstand the bulk of handling and vibration.
Factors affecting adsorption. Number 1. Surface area of adsorbent. Larger sizes imply a greater adsorption capacity. Number 2. Particle size of adsorbent. Smaller particle sizes reduce internal, diffusional, and mass transfer limitation to the penetration of the adsorbate inside the adsorbent. Number 3. Contact time or residence time. The longer the time, the more complete the absorption will be. However, the equipment will be larger. Number 4. Solubility of solute in liquid. Substances slightly soluble in water will be more easily removed from water than substances with high solubility. Also, non-polar substances will be more easily removed than polar substances since the latter have a greater affinity for water.
We continue on the factors affecting adsorption. The fifth factor is the affinity of the solute for the adsorbent, which is the activated carbon in this case. The surface of the activated carbon is only slightly polar, hence non-polar substances will be more easily picked up by the carbon than the polar ones. We just need to remember that the more polar a molecule is, the lesser chances of it being adsorbed. The sixth factor is related to the previous factor, as it says that the more number of carbon atoms a molecule has, the less polar it is, and hence the better adsorption. The seventh factor says the size of the molecule with respect to the size of the pores of the adsorbent affects adsorption. We just need to understand that the smaller the molecules are, the more probability of it being adsorbed. The eighth factor is the degree of the ionization of the adsorbate molecule. We just need to know that the neutral molecules are more readily adsorbed than the ionized ones. And for the ninth factor, we must know that the degree of ionization of a species is affected by its pH, and hence we go back to the eighth factor.
Component adsorption. Early theories were concerned with adsorption from the gas phase. Sufficient was known about the behavior of ideal gas for relatively simple mechanisms and for equations relating concentrations in gaseous and adsorbed phases. At very low concentrations, the molecules absorb or body space over the adsorbent surface so that one molecule has no influence on the other. For these limiting conditions, it is needed to assume that the concentration in one phase is proportional to the concentration in the other. That is, C sub S equals to K sub AC. This expression is analogous to Henry's law for gas-liquid systems.
The Langmuir isotherm. At higher gas phase concentrations, the number of molecules absorbed soon increases to the point at which further adsorption is hindered by lack of space on the adsorbent's surface. The rate of adsorption then becomes proportional to the empty surface available, as well as to the fluid concentration. At the same time, as molecules are adsorbing, other molecules will be desorbing if they have sufficient activation energy.
In this slide, we are given two formulas to be used for the Langmuir isotherm. Specifically, it is for the adsorption which is confined to a monomolecular layer. In the two formulas, AO stands for the fraction of the empty surface, A1 stands for the fraction of the surface occupied by a monolayer of adsorbed molecule. BO is the ratio between two variables which are KO, which stands for the velocity constant for adsorption onto empty surface, and K1 prime, which is the velocity constant for desorption from a monolayer.
Equation 17.2 has been developed for adsorption from the gas phase. It is convenient to also express it in terms of partial pressures, which gives equation 17.3, where Cs is the concentration of the adsorbed phase, Csm is the concentration of the adsorbed phase when the monolayer is complete, B1 is equal to BO over RT, and P is the partial pressure of adsorbate in the gas phase.
Previous equations have the form of the Langmuir equation and assumes that these are no interactions between adjacent molecules on the surface. The energy of adsorption is the same all over the surface, and the molecules adsorb at fixed size and do not migrate over the surface. When B1P is much greater than 1, equation 17.3 reversed into the form of Henry's law and can be written in linear form to give this formula, so that a plot of P over S against P will be a straight line when applied to a system that behaves in accordance with the Langmuir isotherm.
In 1938, Brunauer, Emmett, Teller, and DeWitt developed what is now known as the BET theory. As in the case in Langmuir's isotherm, the theory is based on the concept of an adsorbed molecule which is not free to move over the surface, and which exerts no lateral forces on adjacent molecules of adsorbate. The BET theory does, however, allow different numbers of adsorbed layers to build up on different parts of the surface, although it assumes that the net amount of surface which is empty or which is associated with a monolayer, bilayer, and so on, is constant for any particular equilibrium condition. Monolayers are created by adsorption onto empty surface and by desorption from bilayers. From the kinetic theory of gases, the frequency is proportional to the pressure of the molecules.
Desorption is an activated process. If E sub 1 is the excess energy required for 1 mole in the monolayer to overcome the surface forces, the proportion of molecules possessing such energy is E raised to negative E sub 1 over RT. Hence, the rate of desorption from a monolayer may be written as where A1 prime is the frequency factor for monolayer desorption. The dynamic equilibrium of the monolayer is given by, where A sub 2 prime is the frequency factor for description from a bilayer, thus creating a monolayer. Applying similar arguments to the empty surface, then
So from the equations 17.5 and 17.6 from the previous slide, we obtained the following formulas. And we must remember that the BET theory assumes that the reasoning used for one or two layers of molecules may be extended to n layers. It argues that the energies of activation after the first layer are all equal to the latent heat of condensation. Hence we have the formula E2 is equal to E3 is equal to E4 up until E to the n, which is equal to the latent heat of condensation.
Hence, it may be assumed that beta is constant for layers after the first, and AI is equal to beta raised to I minus 1 and A1, or B2 beta raised to I AO, where B2 is equal to alpha O over beta, and AI is the fraction of the surface area containing I layers of adsorbate. Since AO, A1 are fractional areas, their summation over n layers will be unity, and 1 will be equal to equation 17.9. The total volume adsorbate associated with unit area of surface is given by equation 17.10, where Vs raised to 1 is the volume of adsorbate in a unit area of each layer.
Since V1s does not change with n, a geometrically plane surface is applied. Strictly, equation 17.10 is not applicable to highly convex or concave surfaces. Equation 17.9 and 17.10 may be combined to give this formula, equation 17.11. The numerator of equation 17.11 may be written as this formula.
and the denominator as follows. Substituting these values into equation 17.11 and rearranging gives, on a flat unrestricted surface, there is no theoretical limit to the number of layers that can build up. When n is equal to infinity, equation 17.12 becomes,
When the pressure of the adsorbate in the gas phase is increased to the saturated vapor pressure, condensation occurs on the solid surface, and V sub s where V sub s1 approaches infinity. In equation 17.13 in the previous slide, this condition corresponds to putting beta is equal to 1. It may be noted that putting beta is equal to 1 over 1 minus B sub 2 is not helpful. Hence, we have the equation 17.8 from the slide I discussed earlier. 1 is equal to K1 over A prime sub 2 times E raised to the quantity of lambda m over RT times P naught, where lambda m is the molar latent heat and P naught is the saturated vapor pressure.
Hence, from equation 17.8, beta is equal to P over PO. Equation 17.12 may be rewritten for unit mass of adsorbent instead of unit surface. This is known as the limited form of the beta equation, which is equation 17.14, where Vs raised to 1 is the volume of adsorbate contained in a monolayer spread over the surface area present in unit mass of adsorbent. When n is equal to 1, adsorption is confined to a monolayer, and equation 17.14 reduces to the Langmuir equation. When n is equal to infinity, P over P raised to O raised to n approaches 0, and equation 17.13 may be rearranged in a convenient linear form to give equation 17.15, where V and V1 are the equivalent gas phase volumes of Vs and Vs raised to 1. If a plot of the left-hand term against P over P raised to O is linear, the experimental data may be said to fit the infinite form of the beta equation. From the slope and in the intercept, V raised to 1 and V2 may be calculated.
The advantage of equation 17.14 is that it may be fitted to all known shapes of adsorption isotherm. In 1938, a classification of isotherms was proposed which consisted of the 5 shapes shown in figure 17.5, which is taken from the work of Brunauer. Only gas-solid systems provide examples of all the shapes, and not all occur frequently. It is not possible to predict the shape of an isotherm for a given system, although it has been observed that some shapes are often associated with a particular adsorbent or adsorbate properties. Charcoal, with pores just a few molecules in diameter, almost always give a type 1 isotherm. A non-porous solid is likely to give a type 2 isotherm. If the cohesive forces between adsorbate molecules is greater than the adhesive forces between adsorbate and adsorbent, a type 5 isotherm is likely to be obtained for a porous adsorbent and a type 3 isotherm for a non-porous one.
Some systems, 3 stages of adsorption may be discerned. In the activated alumina air-water vapor system at normal temperature, the isotherm is found to be type 4. This consists of 2 regions which are concave to the gas concentration axis separated by a region which is convex. The concave region that occurs at low gas concentration is usually associated with the formation of a single layer of adsorbate molecules over the surface. The convex portion corresponds to the buildup of additional layers, whilst the other concave region is the result of condensation of adsorbate in the pores, so-called the capillarity condensation. So we have now the graph here, the amount absorbed versus the relative pressure.
At low gas concentrations, while the monolayer is still incomplete, the absorbed molecules are relatively immobile. In the multilayer region, the adsorbed molecules behave more like a liquid film. The amount of capillary condensation that occurs depends on the pore sizes and their distribution, as well as the concentration in the gas phase. When n is equal to 1, equation 17.14 represents a type 1 isotherm. When n is equal to infinity, equation 17.14 represents a type 2, and the rarer type 3 isotherm by choosing a suitable value for B2. As B2 is increased, the point of inflection or knee of type 2 becomes more prominent. This corresponds to the increasing tendency for the monolayer to become complete before a second layer starts. In the extreme case of an adsorbent whose surface is very uniform from an energy point of view, the adsorbate builds up in well-defined layers. This gives rise to a steep isotherm, in which each step corresponds to another layer. When B2 is less than 2, there is no point of inflection, and type 3 isotherms are obtained. The condition 1 is greater than B2 is greater than 0 often corresponds to a tendency for molecules to absorb in clusters rather than in complete layers. The success of the BET equation in representing experimental data should not be regarded as a measure of the accuracy of the model on which it is based. Its capability of modeling the mobile multilayers of a type 4 isotherm is entirely fortuitous because, in the derivation of the equation, it is assumed that adsorbed molecules are immobile.
We have now the sample problem we are going to solve. Spherical particles of 15 nanometer diameter and density of 2,290 kg per meter cube are pressed together to form a pellet. The following equilibrium data were obtained for the adsorption of nitrogen at 77 Kelvin. Obtain the estimates of the surface area of the pellet from the adsorption isotherm and compare the estimates with the geometric surface. The density of liquid nitrogen at 77 K is 808 kg per meter cube, and the data in the table below gives the data for P over P naught and the volume of liquid nitrogen in meter cube over the kilogram solid, where P is the pressure of the sorbate and P naught is its vapor pressure at 77 K. So we will use the following data to solve the problem. First, the density of the liquid nitrogen is equal to 808 kg per meter cube. The area occupied by one adsorbed molecule of nitrogen is 0.162 nanometers squared, and the Avogadro's number, which is 6.02 times 10 to the power of 26 molecules per kilomole.
We need to find the total surface area in meter squared per kilogram using the BET isotherm and the total volume in meter cube per kilogram using the Langmuir isotherm.
Solution: for 1 meter cube of pellet with a voidage E, then the number of particles equals to 1 minus epsilon over pi over 6 times the cube of its diameter. For the surface area per unit volume, that will be equal to 6 times 1 minus epsilon divided by its diameter. 1 meter cube of pellet contains 2 to 90 times 1 minus epsilon kilograms solid, and hence the specific surface will be equal to 1.747 times 10 to the 5th meter squared per kilogram. And using now the BET isotherm, we will use now the equation 17.15, where V and V prime are the liquid volumes of adsorbed nitrogen. From the adsorption data given, The third and the fourth row was calculated based from it. And then plotting P over P naught divided by the quantity V times 1 minus P over P naught against P over P naught as shown in figure 17.6. Then the intercept 1 over V prime B is equal to 300 and the slope B minus 1 over V prime B would be equal to 13,902. So the figure 17.6 is showing you the graph of your adsorption isotherms, the Bethe isotherm and the Langmuir isotherms in this problem.
From which V is equal to the quantity of 13,902 over 300 plus 1 is equal to 47.34, and the V prime is equal to 1 over the quantity of 300 times 47.34 is equal to 70.4 times 10 to the negative 6 cubic meter over kilogram. Substituting the values, the total surface area is equal to 2.040 times 10 to the 5th square meter over kilogram.
So now we will be solving the problem using the Langmuir form of the isotherm. So this assumes that this applies at low concentration, and then expressing the pressure as the ratio P over P naught and the amount adsorbed as the volume of the liquid adsorbate. So we modify the equation 17.4 to be P over P naught over V is equal to P over P naught over V prime plus 1 over B sub 2 V prime. So it follows the equation of the line y equals to mx plus b. So in this case, we will have the y as P over P naught over V, and our x as P over P naught, and our slope as 1 over V prime. So we will recalculate the values from the table given from the problem and plotting it on a graph. And we will obtain the slope as 1 over V prime, which is 13,902, and calculating for V prime, we obtain 71.9 times 10 to the power of negative 6 meter cubed per kilogram, which agrees or which coincides to the value we obtained from using the BET isotherm. It may be noted that the areas calculated from the isotherm are some 20% greater than the geometric surface, probably due to the existence of some internal surface within the particles.